And so begins Lecture 6 on continuous maps. Once again, one of the interesting aspects here is that our definitions of continuity here will not be based on distance. They'll be based on sets and a given topology. So let's get into it. So here it is. X and y topological spaces, f a function from x to y. F is continuous if the inverse image of A, all right, which is defined to be x and x, such that f of x is an A, if that's open in x for any open A and y. In other words, continuous function is one for which the inverse image of open sets is open. All right. Now, you can also call an inverse image a preimage if you like, and some of you want to make a distinction between those, but I think the terminology inverse image is pretty universal, so I'm going to use inverse image. Although I think Minetti uses preimage, which is, fine, whatever. Let's see here. So, theorem, f from x to y is continuous if and only if the inverse image of all closed sets is closed. So apparently we could have used closed sets to define continuity. Also, f is continuous if and only if the inverse image of any, basis if you have a basis for topology, if the inverse image of anything in the basis for y is again open. So it suffices to check inverse image of closed is closed, or if you have a basis handy, if you can check that the inverse image of arbitrary sets in your basis for your topology are open, that will also do. Okay, here's the proof of that. All right, so let me just, I'll scooch in here just a bit. All right, and forgive me while I go grab my tea right quick. So, I'll be back. Feel my voice starting to go. I think I need to drink something here. I should have put some honey in it. Oh well, it's too late. Come on. This tea bag's misbehaving. Yeah. All right, so suppose, let's prove one. Suppose f is continuous, all right, and we've got a closed set. That means that the complement of y by c is open in y, right? Definition of closed is that the complement's open. Thus, the inverse image of y minus c is x minus the inverse of c. That's a property of inverse image. This right here, property of inverse image. But then, let's see here. So that's open, right? So that means that since f is continuous, the inverse image of this is open, which means that this is open. But if this is open, that means that the inverse image of c is closed, by definition of closed in x, right? And that's what we wanted. We took a closed set, and we showed its inverse image was closed, and the main data we needed to prove that was the set theory identity for inverse images, paired with the fact, the definition of continuity, that the inverse image of an open set is open. Okay, so there's that. How about the other direction? Suppose that the inverse image of a closed set is closed in under f, right? So closed in y implies f inverse of c is closed in x, all right? What I want to then do is show that f is continuous. How do I do that? I need to show that the inverse image of open sets is open. So to do that, I must take an arbitrary open set in y. Okay, let me scooch this over here a bit. So let A a subset of y be open. Then y minus A is closed because the complement of y by y minus A is just A again, and that's open. So that makes y minus a closed. And so then, but then since y minus a is closed, we know that the inverse image of y minus a is again closed by assumption, right? And if this is closed, that means that the inverse image of a is open, because that's the complement. Well, I'm not sure that this is terribly relevant, but oh, I guess I need to know that. So if this is closed, that means its complement is open, right? So what is the complement of this? It's x minus that, right? But that's equal to f inverse of a again. So, which is open again because this is closed. And so we've shown that an arbitrary open set has an inverse image which is open. Consequently, we have shown that f is continuous. And claim 2 here follows from the similar identity here that the inverse image of a union is the union of the inverse images. All right, so I'll let you guys look more at that, but that's a useful thing to know. We can check continuity of a map by checking the inverse images of a basis. That will do for us. All right, lemma 3.25. All right, what do we got? Lemma 3.25 here, page 2, is that let f from x to y be a map between topological spaces. F is continuous if and only if the image of the closure of A is a subset of the closure of the image of A for any subset A of x. All right, let's prove it. So first of all, if f is continuous and A is a subset of x, then to say that f of A is then f of A closure is closed. All right. How do I know that? Well, that was basically one of the properties of the closure, is that the closure of a set is a closed set, right? Anyway, and hence the inverse image of that is closed, right? By the previous thing we just proved that the inverse image closed is closed. For a continuous map, we're assuming f is continuous here. So this is closed, and it also contains A, right? Which means that the closure of A has to be a subset of the inverse image of the closure of f of A. It's hard to verbalize this stuff, which implies that the image of the closure is a subset of the closure of the image, which is what we were trying to prove. And then the converse direction, if we know that the image of the closure is a subset of the closure of the image for any subset A of x, if we take C a closed subset of y, that means that C bar is equal to C, among other things. And so if we let A be the inverse image of C under F, then if you look at it, let's see here. Okay, so then we took this C, we're constructing A as the inverse image of this closed set, right? Then F of the closure of the inverse image of C is a subset of F of the closure of F of the F is the subset of the closure of F inverse of C, right? This right here, I'm using the assumption right here in the case that A is equal to F inverse of C, okay? But this is just equal to C, the closure of C again, which by the way is equal to C. So what's that show us? Thus, the closure of the inverse image of C is a subset of F inverse of C, but on the other hand, we also know that the inverse image of C is a subset of its closure. So if you have this containment and that containment, you got equality. So the closure of the inverse image of C is equal to the inverse image of C, which is to say that the inverse image of C is closed. Consequently, the inverse image of an arbitrary closed set is closed, which shows us that F is continuous. All right, there you have it. So just a remark here. The image of the closure being a subset of the closure of the image means that points which adhere to A map into a subset of the points which adhere to f of A. So this is very much in line with what we were talking about in definition 1.4, where we were talking about continuous maps are ones which kind of don't tear the space, right? The points which are stuck together to start with are still stuck together after you map them under this continuous map, all right? It doesn't tear things. All right, 3. Oh, this one's nice. This one's nice. I was always happy as a student of topology to see this on like a test. Prove the composite of continuous functions is continuous. It's actually not too bad here. So if we have f from x to y and g from y to z, both continuous maps on topological spaces, then the composite g composed with f is continuous. All right, so if we have g composed with f from x to z, be defined as usual by g of f of x as g composed with f of x is g of f of x for all x in x, and suppose that u is open in z. We would like to show that the inverse image of u is again open in x. All right, so suppose f and g are continuous. Since g is continuous, right, and g is still assuming up here that it's going from y to z, right? Since g is continuous, the inverse image of this open set is itself an open subset of the domain of g, which is y. All right, so we've got this open set in y by the continuity of g, but we can look at the inverse image of that g inverse of u. Well, that's the inverse image of an open set, which is open, also by the continuity of f. So we have f inverse of g inverse of u as an open set. But on the other hand, we can also prove that the inverse image of the composite is the image of the, it's this right here. It's the inverse image of f of the inverse image of g of u. And so because of this set theoretic identity, and so like this formula is true, and sometimes referred to as the Shocks-Shoes formula for like, in group theory or perhaps the proofs course. When the inverse functions of f and g exist, this continues to be a true identity, just even at the level of inverse images of sets. So even when the inverse functions don't exist, this still holds true. I'll prove it down here. So anyway, that lemma aside, we've shown that the inverse image of an arbitrary open set here is in fact open over there, and as such the composite is continuous. Yay! All right, so here's that lemma, which I guess I haven't called the lemma, but here's why it is true that this is equal to that. All right, so let x be an element of the inverse image of g composed with f of u. That means that g composed with f of x is in u, which means that g of f of x is in u. That means then that f of x is in the inverse image of u under g. And so x is actually an element of the inverse image of f of the inverse image of g of u. Therefore, we have that the inverse image of the composite is a subset of f inverse of g inverse of u. Likewise, on the other hand, if I take a point in here, if x is in f inverse of g inverse of u, that means that f of x, right, is an element of g inverse of u by definition of inverse image. And then that means that g of f of x is an element of u by definition of inverse image of g. And so that shows you that g composed with f of x is an element of u, which is to say that x is an element of g composed with f inverse of u. And so this is a subset of that. We have containment both ways, therefore these sets are equal. And again, none of this requires that f inverse or g inverse be functions. Now, I realize I'm going kind of fast through these things. And if you don't understand them, it's because you haven't yet fully absorbed the definition of inverse image. And it's a struggle, all right? Still a struggle to me to this day. When I'm tired, I can get turned around on it. So you gotta do what it takes to to just really learn that definition of inverse image. All right, it's really important to this course and really to most of high-level math. And it's one of those things that really separates good math majors from math majors who struggle and struggle and struggle. But, you know, it's something we can all learn, I think. Anyway, so moving along. A map F is continuous at a point. This is a definition, okay? A map, what do we mean by continuity at a point? It's kind of funny. We've turned the tables, right? In calculus, we define continuity at a point first, right? And then we define continuity on a set to mean that it's continuous at each point in the set, right? Now the tables have turned. We started by defining continuity for the function on its whole domain, and now we're specializing to continuity at a point. So it's kind of funny, isn't it? Not funny, haha, like funny strange. Okay, so continuous at a point P, if for any neighborhood U of f of P, there is a neighborhood V of P such that f of V is a subset of U. So I think you could recast this definition in terms of inverse images if you wanted. It's, you know, f inverse of, so V is a subset of f inverse of U, I believe. I think it's saying that the inverse image, that there's a neighborhood in the domain in the inverse image of any neighborhood in the range, right? All right, anyway, this is the definition, so it is what it is. Here's a kind of a horrible picture of it. You've got a point P, you got f of P over here. You take a neighborhood f of V of P, like this, right? Then there is some neighborhood U over here, such that the f of V is a subset of that, right? That is, in other words, the inverse image of this guy. It goes back and it contains, I think it contains V over here. But anyway, f of V is a subset of U. There it is. All right. Theorem. A map F is continuous if it is continuous at every point of X. Well, that's nice. I mean, that was a definition in calculus. Now it's a theorem here. Okay. So let's see how we prove it. All right, so here it goes. Suppose F is continuous and let P be a point in its domain. Suppose U is a neighborhood of f of P in the codomain. All right. I guess technically it's in the range because it's f of P, right? But anyway, by definition of neighborhood, there exists a open in Y for which f of X is an element of A. All right, which is a subset of U. I think that's a typo. I think that X, I meant to make a P. I'm going to put a P right there. I believe that's supposed to be a P. X just mysteriously appeared right there, you know, from the thin air. It wasn't anywhere before. Neighborhood of P, I believe, should be here as well. Sorry about that. All right. Definition of, so we have U is a neighborhood of f of P and Y. By definition of neighborhood, there exists an open subset inside the neighborhood, right, which contains the point in question, in this case f of P, and V is, notice that V, let's see here, oh, and it's open, right? So if we let V be the inverse image of A, then since f is continuous, that means that f inverse of A is open in X, right? And that also, you can see that V will serve as a neighborhood of P, all right? And it has f of V as a subset of U, and therefore f is continuous at arbitrary P and X. So we've just shown that the condition for continuity at a point is met if we just use continuity and follow a point, all right, in the neighborhood and such. Likewise, the other direction, if we have continuous at every point in X, if we have A as a subset of Y as an open subset, let me scooch it up here a bit. So suppose you have an open subset in the codomain rather, and if we let X be an element of the inverse image of A, then A is a neighborhood of f of X, all right, and hence there exists a neighborhood V of X for which f of V is a subset of A, which then means that we can say V is equal to f inverse of A, and we can show that f inverse of A is a neighborhood of X, but since X was arbitrary, we can conclude that f inverse of A is open. Therefore, f is continuous. So this is referring back to that characterization of open sets that every we have a neighborhood around every point in the set, then that makes the set open. So it's using that characterization of open that we had earlier. But there it is. So, you know, whatever. I'm still. I mean, I'll be honest with you. I'm more of an analyst, I guess. I do prefer limiting the limiting way of thinking about continuity over this. This to me is, you know, it's not native to my mind, but there it is. I mean, you know, continuity at a point versus continuity on the whole set. There it is. All right. Now back to Now we talked about homeomorphism in chapter 1, but there it was in the specific confines of mappings on Euclidean space, Rm to Rn or whatever. Now we're talking about homeomorphisms in the wild, all right? So suppose you have a homeomorphism is a continuous bijection with continuous inverse. That is a continuous map F from X to Y. That is a homeomorphism if there exists a continuous map G from Y to X such that the composite of F and G is the identity on Y, and the composite of G with F is the identity on X. What this is saying is that F and G are inverses of each other, all right? And they both have to be continuous. So a homeomorphism is a continuous map with continuous inverse, all right? If there exists a homeomorphism from X to Y, then we say that X is homeomorphic to Y. And we had tons of interesting and sometimes weird examples of that in chapter 1. I would encourage you to go back and look at those afresh and anew. So, I mean, this is one of the big projects of topology, is like, given two topological spaces, are they homeomorphic? I mean, this is one of the central questions of topology. How do you decide when two topological spaces are homeomorphic? Much of our time and energy in this course is really spent towards developing tools, artifacts, if you will, of the space, which we can calculate and decide whether or not two given spaces are in fact the same topological space in disguise, if there is actually a homeomorphism which takes one to the other, right? So homeomorphism in this context is the analog of isomorphism in, let's say, linear algebra. Two vector spaces are isomorphic. Let's say two finite dimensional vector spaces are isomorphic if they have the same dimension. That's the dimension theorem. And there's other interesting things about linear algebra that I should pause and mention. Interestingly, in linear algebra, if we have a function which is a bijection, all right, between vector spaces, if you have a bijection between vector spaces and it is linear, linear in that context would be the analog of continuity, okay? If you have a bijection between vector spaces, which is linear, it is a theorem of linear algebra that the inverse is automatically linear. We have no such privilege here. Continuity of the forward map does not guarantee continuity of the inverse map. I don't think I have an example handy to show you how that can get ruined, but examples exist. All right, so let me continue on here. A function f is called open if it maps open sets to open sets. Notice that this is a forward image, so we're automatically guaranteed that inverse image of open is open for a continuous map, but we are not guaranteed that the image of open is open for a continuous map, actually. A closed map maps closed sets to closed sets. Again, for a continuous map, we're guaranteed the inverse image of closed is closed, but we're not guaranteed that the forward image of closed is closed. And that is for a reason. That is because that these, well, we have this, equivalence right here. F from x to y, a continuous map, the following are equivalent. F is a homeomorphism. All right, this isn't, precondition here is that F is continuous, okay? But given that backdrop, we have that F is a homeomorphism is equivalent to F is closed in bijective, or F is open in bijective. Okay, so like, and it's once you think about it for a second, it's kind of silly because F being closed is essentially tantamount to saying that the inverse image for the inverse map takes closed to closed, and the inverse image for the inverse map takes open to open. So that this is just a kind of thin veneer over the continuity of the inverse map. But let's elaborate on that a bit, okay? 1 implies 2. So the logic we're going to do is 1 implies 2, 2 implies 3, 3 implies 1. That gives you equivalence of all three, right? So let F be a homeomorphism, then F is bijective, all right? And if C is closed, notice that F of C, and so like bijective is nice because that means you got the inverse map to work with. And man, when you have the inverse map to work with, you got all kinds of cool formulas at the handy. So I can rewrite F as the inverse of the inverse in this context, right? And F is homeomorphism, so its inverse map is continuous, right? So we've got a closed set, the inverse image of a closed set under a continuous map. Well, that's closed since F inverse is continuous. And so we have shown that the image of a closed set is closed, which is to say that F is closed. And we already assumed it's bijective. So like so this was assumed by bijective, so it's still bijective. Yay! All right, great. 2 implies 3. Here we go. Let me zoom in a bit as my writing has gotten a little bit tiny. All right, sorry. Been teaching Hannah calculus in a Russian accent lately. It may be rubbing off into my other classes. I don't know. All right, so let F be closed and bijective. All right, we want to show F as open map. So if A is an open set in X, the complement of X by A is closed, right? And because of course X minus C is A again. So F of C is closed because we're assuming that F is a closed map, right? And that means that Y minus F of C is open. Okay, great. But F as a bijection gives that F of A is F of X minus C, which is actually Y minus F of C, which is to say that F of A is open because it's, Y minus F of C was closed, right? So if you take the whole space minus a closed set, remove a closed set, you get an open set. So the F of A is open, and so we just showed open maps to open, which says F is an open map. All right, 3 implies 1. Suppose F is open and bijective, and let's set G equal to the inverse of F, okay? So if B is a subset of X is open, then G inverse of B is F of B because the inverse of the inverse is the function again, right? And but we're assuming F is open, right? So if B is open, F of B is open. That shows that the inverse image of an open set is open for G, and that means that G is continuous. But if G is continuous, we have that F is a homeomorphism, because we already had that F is a bijective continuous map, and now it has a continuous inverse, so that means F is a homeomorphism. So, all right, so there you have it. Now, as I said, I wanted to work a problem for you guys, and let's see if I can Well, here, let me show you what, let me show you what didn't work, okay? So here's what not to do, all right? Here's what not to do. I'll tell you what you don't do. You don't like sloppily write down a topology problem and try to work it when you're half asleep, because it's just a waste of your time, all right? So here's what I copied down. X from X to Y be a continuous mapping, D a subset of Y, a dense subset, right? The dense means the closure of D as well. Y, great. Prove F inverse of D is dense in X. And I went to work on this. And you know, I got nowhere really fast. And then I said, well, maybe I should go back and look at the book again. And I did that. And you know what I discovered, lo and behold? I discovered that I had missed some important words. All right, so here's what 3.26 actually says. It says let f from x to y be continuous map. So far, so good. All right. Oh, wait a minute. Nope, I've already failed. So I'm copying from 3.25 because I'm a dummy. So 3.26 actually says let f from x to y be an open. It says open. That is very different. Open map, okay? And D a subset of y, a dense subset. Dense subset. And then it says prove that f inverse of D, right, is dense in X. All right, so that is the real exercise 3.26. So you see what I copied down wrong was continuous versus open. As we just said, well, golly, I think we're assuming open maps are continuous. Well, uh-oh, huh. Well, I guess we haven't assumed that an open map is continuous, is it? I mean, in lemma 3.31, we've assumed that it's a continuous map here, and then we've worked in that context, but his definition, he just has a function. He doesn't assume that the function is continuous. Like open just means open maps to open. I guess it's in principle possible to have a map which is open and you know, yet not continuous. Pretty sure that's possible. That's essentially the same as saying you can have a map that is continuous and yet not have a continuous inverse, you know? So if it was open, well, let me shut up. All right, so, So let's see here. Here is my, let me just try to walk us through my scribbling. All right, so first of all, there's two ways to characterize dense. The one is that the closure of the space is closure of the space is a space again, but another useful way is that, you know, D dense means D intersect, let's say, V is not an empty for all non-empty in open sets in Y. Okay, so that's what it means to be dense in Y, is that every non-empty open set it intersects D at least one point, okay? So that's the first thing. And then let me just, I'll try to walk through my argument here and we'll see if it holds together, or we'll see if I've accidentally used continuity of F, because I think I was thinking you could, but I'm not sure I actually used it. Let's see. All right, so let me get my marker, get to work here. All right, so let U be a subset of X, and let's let U be non-empty. All right, then F of U is non-empty. All right, subset, and of course F of U is a subset of Y. Right? Okay, great. Thus, F of U intersect D is non-empty by density of D. All right, so therefore, there exists F of X naught, an element of F of U intersect D. All right, because it's non-empty, there has to be a point in there, and if there's a point in this set, they have the form F of X naught for some X naught in U. All right, thus therefore F of X naught is an element of F of U, and F of X naught is an element of D. All right, what does that tell us? Well, that tells us that X naught, well, I mean this, I didn't need to write that again, I guess, but let me just get to the point here. So X naught is an element of U. I already said that back up here, right? And this right here tells me that X naught is an element of F inverse of D, right? And so what's this all tell me? This tells me that if inverse of D intersect with U is not empty, right? Because there's a point, X naught, that's in both of these guys. And you know what? I did not use the continuity of F here. I did not. Cool. I thought I used it, but I see now that I didn't. I'm thinking of the scribbling I had on the other side of the unproductive page there. That's where I use continuity, and I got nowhere anyway. But look here. So we've taken arbitrary open set in U, in X rather, and we've showed that that non-empty open subset of X necessarily intersects the inverse image of this dense set, right? And what does that prove? That proves that therefore F inverse of D is dense in X. So I haven't, now that I have adjusted the problem to like as it's actually stated in the book, I haven't tried the other way of thinking about closure in terms of, you know, it's the intersection of all closed sets which contain the set. But I imagine that way of trying to do this problem would be more complicated. So I guess it's important to know about this other characterization of dense subset, that it meets every, you know, open set non-trivially. So anyway, hey, that's it for this one, guys. So thanks.